So the next speaker will be Yangyang. Yangyang was my first interaction with composites outside structural applications. I thought it taught me about composites and that they are much wider than just aerospace structures. They are fundamentally multi-physics problems, and Jan works on the cross-section of electrophysics, chemistry, material synthesis, where composite materials are used for sensing applications. Go ahead, Yangyang.
Good afternoon, everyone. I'm the PhD student of the Professor Giles. My research point, my intriguing point is about the design of the cerebral electronics. Okay, let's come back to my presentation today. Previously, we designed a cerebral temperature, totally stretchable temperature sensors. As we all know, that's the temperature sensors we use. It's almost based on the competence of the routines with the sensor. The drawbacks of this sensor that is really hard to make them stretchable, and also have the after the influence of the large strings. So we think about how could we solve this problem. We use the Seebeck effect to design the totally stretchable temperature sensor. Like that showed in the figures. We use 2 nanomaterials. For example, the silver nanowires or the carbon nanotubes to make it to a U-shape style temperature sensor. Because of the 2 the Seebeck coefficient of this 2 nanomaterial is different. So we can, if there exists the temperature difference between the bottom and the top of the U-shape, so we can got output voltage. This voltage is called the Seebeck voltage, and this is dependent on the temperature difference between the top and the bottom. We use the ink printer to print the nanomaterial solution in the nano filter, and then we transfer the printed U-shape sensing layer to the PDMS substrate, and then we remove the filter, just left the PDMS and also the nanomaterial we print. We think without the parameter, we think about the Seebeck coefficient should be the Seebeck coefficient changed with the strain should be have 2 cases. Like shown in the F figures. The first one is that the Seebeck coefficient of these 2 nanomaterials is stable with the strain. And then another one is that the Seebeck coefficient changed with the strain. So I think it's better. It's better that the Seebeck coefficient doesn't change with the strain. So that means the temperature sensor should be strain-insensitive of the strain. So in the left figures, we show that the performance of this temperature sensor and the different temperature grade. For example, in the figure A, we can see that the output voltage is almost linear with the applied temperature difference, and also the strings, and also the string have nothing influence on the performance of this temperature sensor. So we think this temperature sensor is really influenced by the string. So this temperature sensor, I think it's good to solve the string polluted problem. And also we test the different nanomaterials. For example, in the figure A, it's multiple carbon nanotube, and also with silver nanowires. And then in the figure B, it's about the single wall carbon nanotube and zero nanowires. We see most we see, and also in the figure C, it's about the multi-wall and single wall carbon nanotubes. So we see is the Seebeck coefficient of these three category temperature is different, but all of them are strain-insensitive. And also another very important factor is about this is the repeatability between different samples. So we fabricated 5 samples with each of the about 3 categories samples, and also we can see all of the samples are almost overlapped. The performance are almost overlapped. So that means the repeatability between the different samples is really good. But the errors is bigger than the information of the strain. That's why, because when we did the experiments, I think it exists error to measure the temperature. So I think, and also I didn't show it here, but we fabricated a large scalable electrode screen to monitor the temperature distribution on a deformable surface as the electrode screen.
Yes, Fernando, Professor Fernando has a question. Go ahead.
Sorry, I'm just struggling to see with my varifocals the data you present on the right-hand side. You've got delta T, I think, on the x-axis and voltage on the y-axis. How do you say it is strain-insensitive measurements?
For example, in the figure A, you see it's five samples. No, it's 1 sample, but the test and the different strain levels. For example, 0 strain, 10% strain to the 40% strain. You see, this is right.
Okay. Thank you.
So all the lines are overlapped. So that means the strain have no influence.
Oh, interesting. How do you make sure that your nanoparticles are trapped in your film?
Some are trapped in the film. You mean?
Yeah, to make sure they don't come out.
You don't know what?
So that they don't come out.
Because for example, when we peel off the filter, so the nanomaterial adhesive on the substrate, and then we covered another layer of the PET mass to embed the nanomaterial in the middle of the substrate.
Thank you.
And also, if the nanomaterial is not very easy, is not very thick, it's also because of I think some nanomaterial can penetrate to some part of the substrate. So the interface is really strong.
Thank you.
Thank you.
Thank you, Yangyang.